This is video 6 for rotation. So for this one we're going to talk about angular momentum. Now for some knowledge, a torque exerted on an object can change the angular momentum of an object. Remember that momentum is a mass times a velocity. So if we take a look at, changing its velocity, we're kind of changing its position. We can also find momentum by taking a force multiplied by a time. And since a torque is the rotational equivalent of a force, if a force can change an object's momentum, then a torque can change an object's angular momentum. So angular momentum itself is a vector quantity, and its direction is determined by the right-hand rule. So we'll go over that again. The magnitude of the angular momentum of some sort of point object around an axis can be calculated by multiplying the perpendicular distance from the axis of rotation to the line of motion. So we'll cover that again. The magnitude of angular momentum of an extended object can also be found by multiplying the rotational inertia by its angular velocity. We'll cover that as well. And then the change in angular momentum of an object is given by the product of the average torque and the time the torque is exerted. So that's a lot like how the change in linear momentum is equal to force multiplied by time. The impulse momentum theorem, really. Okay, so linear momentum, let's review that. It's the product of mass and velocity. So momentum was mass times velocity. I have the P and V boldface because they're vectors. So thinking about the correlation between translational and rotational, we can find that the angular momentum then, we use L for angular momentum, equals the rotational equivalent of mass, which is moment of inertia, and the rotational equivalent of velocity, which is angular velocity. So this is how we calculate angular momentum. It's kind of like P equals M times V. We can also take a look at Newton's second law. The net force equals the change in linear momentum with respect to time. Well, the rotational equivalent of force is torque. So we can have an expression for the amount of torque, or the amount of net torque acting on an object by looking at its change in angular momentum. And I can go into the realm of calculus by changing those deltas into lowercase d's for derivatives. Now, for conservation of angular momentum, just like we had with conservation for momentum, we also have a conservation law for angular momentum. So for linear momentum, we saw that the change in momentum for object 1 plus the change in momentum of object 2 as they interact should equal 0. Well, we're going to have the same thing. So similar, I write down the wrong letters. Now this change in momentum for 1, change in momentum for 2, that related to the fact that the sum of all initial momentum had to equal the sum of all final momentum. So if I had two objects, object 1 and object 2, likewise, I can get the same thing. Now this conservation law helps us explain why rotating bodies undergo an angular acceleration when the placement of the mass changes. So I want you to think of an ice skater. As she pulls in her arms during her spin, her angular velocity increases. And you might have done this just kind of playing around. And it's because she's changing her moment of inertia. Now, conservation of angular momentum can also be used in astronomy and playgrounds. So let's take a look at a couple examples here. Halley's Comet. It has a 75 to 76 year period. Halley's Comet follows an elliptical orbit around the Sun, with its closest position being 0.6 AU and its farthest position being 35 AU. So I'm probably throwing around some terms you might not have heard yet. AU means astronomical unit. 1 AU is the average distance between Earth and the Sun. So if I were to take a look at that, the Earth's orbital radius, or average orbital radius about the Sun, that would be 1 astronomical unit. So Halley's Comet gets closer to the Sun than the Earth does, and it gets about 35 times farther away from the Sun than the Earth does. So let's make a picture of this. So here's the Sun, and here's Halley's Comet's path. So it's elliptical, so it gets real close and gets really far away. So when Halley's Comet's right here, it's 0.6 AU. When Halley's Comet's out here, it's 35 AU. When it's at its closest position to the Sun, it's traveling roughly at a velocity of 70.56 kilometers per second. What I would like to know is, how fast is it traveling at its furthest position away? So to do this, we can use conservation of angular momentum. So first off, the definition of momentum is I times omega. And what I can do is I can start putting in some bits into this. First off, I. Well, Halley's Comet, I can think of this as a point mass going around an axis. So the moment of inertia for a point mass is mr squared. Now, since I have v's, I want to get rid of that omega. So v equals r times omega, so omega would equal v divided by r. So the moment of inertia then for Halley's Comet, notice that we have some canceling here, is mrv. Conservation of angular momentum tells us that the change in object 1's angular momentum plus the change in object 2's angular momentum equals 0. Well, I only have one object, so I can get rid of this term right here. So that means that the change in Halley's Comet's angular momentum must equal 0. Well, that means final minus initial. Well, that basically means that Halley's Comet's final momentum must equal its initial momentum. So we have mass times final radius times final velocity equals mass times initial radius times initial velocity. And again, we have some canceling. The masses go away. And I get this nice little relationship. Final radius times final velocity equals initial radius times initial velocity. So velocity then, the final velocity would equal that right there. So now we just have to plug in our values. So the initial radius is 0.6, the initial velocity is 70.56 kilometers per second. Divide that by 35, and what we get is it's right around 1.2 kilometers per second. So as you might imagine, it gets slower as it gets farther away, and then it speeds up as it gets closer. We can also use conservation of energy to help us explain that. As it's getting farther and farther away, it's getting, if we think about the whole energy of the system being the same, its potential energy is kind of like increasing and its kinetic energy is decreasing. When it gets closer to the Sun, its kinetic energy increases and its potential energy decreases. So we can also use conservation of energy to help us explain some of this. The next problem I want to look at is a playground, and specifically a merry-go-round. And let's say it's spinning with negligible friction. the child, let's say there's a child that's moving from the very center out to the rim of the merry-go-round platform. So as this merry-go-round child system spins, the child, because the child's moving, the moment of inertia will be changing. Let's make a picture of this. So here's the merry-go-round. Here's the child moving from the center to the outside. And let's say it's, keep it positive, so let's say it's spinning counterclockwise. All right. Merry-go-round has a radius of 1.3 meters, mass of 100 kilograms. The child has a mass of 30 kilograms. The merry-go-round is initially spinning at 1 revolution per minute. What will be its rotational speed when the child reaches the rim? Now, since the child's mass is going to the rim, I predict that it will be less than 1 revolution per minute. All right, so let's get some stuff down here. We have two objects that are going to have angular momentum. The merry-go-round and the child. The merry-go-round is a solid disk, so I'm going to say the moment of inertia for a merry-go-round. For a solid disk, it's 1/2 mass r squared. The child is a point mass, so the moment of inertia for the child is just going to be m r squared. So applying conservation of angular momentum, the change in momentum for the merry-go-round plus the change in angular momentum for the child must equal 0. So for the merry-go-round, it's final minus initial. I would have that. Now, notice that for the merry-go-round, the only thing changing is its angular speed. Its moment of inertia stays the same. For the child, however, the child's moment of inertia is changing. All right, now let's think about this. The omega, I didn't bother putting an m or a c beside the omega because the child's attached to the merry-go-round, so the child merry-go-round system will share final initial angular speeds. The initial moment of inertia for the child will be 0. The reason for that is because the child is starting at the very center of the merry-go-round. So the child's initial radius is 0. So that's why that's gone. Okay, now we can go ahead and plug in our moment of inertia formulas. I'm trying to use a capital M for the merry-go-round and a lowercase m for the child. All right. Looking at this, I hope you see that the parentheses could go away. And that's important because we see that the r squareds all cancel. So it doesn't matter what the radius of this is. And I could also do some rearranging here. where I get my final angular speeds on one side and my initial angular speeds on the other. And now I just have to solve this for the final angular speed. There we have it. Notice that the 1/2 capital M's do not cancel. It's very important. So when I plug in 100 kilograms for the mass, 30 kilograms for the mass of the child, 1 RPM for the initial angular speed, I get 0.625 RPMs. So I would see that the merry-go-round does in fact slow down. Alright, we're going to stop there. We'll have one more video to finish out this unit.